To do today. So what I plan to do today is talk about the structure and the function of the synapse. We'd just begun to touch on this last time. We'd just gotten to the point where we're beginning to talk about synapses. And we'd gotten to the idea that Sherrington had invented the term that Langley had described a receptive region for neurotransmitter, mostly at the neuromuscular synapse. And what we want to do today is bring this on to two more ideas. There were a set of experiments that were really pivotal. And these experiments were done in the early 1920s by a guy named Otto Loewi. And Otto Loewi did these experiments on a frog heart. And I opened this story a little bit in the second section, but I didn't get to it here. So we'll start with the Otto Loewi frog heart experiments. And then we'll carry this on from the idea that we then knew that there was the release of neurotransmitter, chemical kinds of communication between a neuron and muscle. But what that really failed to describe was the structure of the synapse itself. That took several more years before they got that squared away. So what I'll try to do is go from the chemistry to a little bit of physiology to some morphology and describe where things stood at that time. And then what I want to do is talk about some more recent work that actually won the Nobel Prize 3 or 4 years ago. And this is the idea of the snare hypothesis. And it turns out that it took years and years and years and lots of molecular biology to begin sorting this out. And I want to tell you a little bit about how this works. Then this whole event, the machinery of neurotransmitter release, is all about exocytosis. It's the machinery, the molecular biology of exocytosis. And then we'll spend a little bit of time on talking about what happens to the neurotransmitter after it leaves the synaptic vesicle and goes out into the synaptic cleft, that space between the pre- and postsynaptic cell. And of course, the things that can happen is the neurotransmitter can bind to a receptor. In some cases, it will just diffuse away. In the central nervous system, the excess neurotransmitter will be taken up by glia. We talked about that briefly the other day. And then we'll see it at the neuromuscular synapse, the special case out in the periphery, that enzymes will break down those neurotransmitters. And this has some implication for actually public policy because it's involved with nerve agents. Then what we'll talk about then is what happens to the neurotransmitter, not only what happens to it, but what becomes the neurotransmitter when it binds to the receptor. This brings us to the idea of the ligand-gated ionotropic channel. And this is a big divide. We've talked about those channels that are opened by voltage or charge. Those are the voltage-gated channels. And then we began talking about the stretch-activated channels out in the periphery and those sensory neurons. Now what we're going to do is go one step farther and begin to think about the ligand-gated channels. These are the neurotransmitter-operated channels. These are the channels that are opened by the neurotransmitter. We've talked about it on the other board. And we'll see that initiates, usually, sodium influx if it's going to be an excitatory postsynaptic potential. And we'll talk about that.